Okay, let's get started today. So the question today was consider the function f from 0 to infinity squared r to r. So then we have this function over here, x and y as the inputs. And then a and b are constant, positive constants, so that's pretty useful. Part A, compute the derivative in Hessian of f. This is pretty standard book work. What I did was I wrote down the function here. I took the partial derivative with respect to x and y, and I got these. I took the with respect to x, y, and xy, and I got these. So then my what is it called? My derivative here would be just f of x, f of y, and then my Hessian would be the fxx, fyy, fxy, fyx. So here we go. So that's part A. And then part B, find the stationary points of F. Justify your answer classifying as a global min, global max, local min, local max, or a saddle point. So we're trying to find a stationary point. So for finding stationary point, the idea is that we're setting the fx equals to 0, right? And fy equal to 0. So all of the partial derivatives should be equal to 0. And then we just rearrange this so that we have this and this. Okay, so that's our first and second equation. If we substitute the second equation in 1, then we would get this expression. And since we know that y is from 0 to infinity, not including 0, so y does not equal to 0, so then I can just um, move the y's on both sides. So then I have 1 is equal to this, so then um, what I get is that my y is equal to this. Next, I know that x is just that thing, so then I just put it back in and I get what x is as well. So then great, I get my stationary point. My stationary point is this thing over here. And for my stationary point, I want to figure out, okay, what kind of thing is it? I want to classify it. So there are kind of three ways to go about this. The first way of classifying is to find the eigenvalues and look at the eigenvalues and see if that works or not. But it's too hard to calculate eigenvalues. It's just too bothersome. Um, if I want, I can also look at what kind of matrix that like this thing is, like semi-definite, positive, definite, so on and so forth. Not the best either. I prefer not to do that. So what I do instead is I can also look at the leading principal minors. That's probably the easiest way, but I didn't think of it at the time. What I did was I first found the determinant, which was 3. So it either told me it's positive, so I know it's either positive definite or negative definite, one of the two. So then I just double checked and did Gaussian elimination. And I got that the two pivots over here, after I do Gaussian elimination, it are both positive. So all of it is positive. So that means that the stationary point is a local minimum. Because I know that the pivots are positive, so then that guarantees me. But leading principal, what is it called? Minors would be easier because I just have to check, okay, this is a single number and it's positive. Great. And then for this, we just check the determinant of this. Okay, great, that works out as well. So as long as we check those two, which is just a simple calculation, it's much easier than the Gaussian elimination way even. So if I was to do this question again, I would definitely use leading principal minors to show that it's a local minimum. And then to show that it's whether or not it's global, we just check the function properties. As x goes to infinity or y goes to infinity, xy goes to infinity, and the other two terms goes to 0 since it doesn't matter. And at x equals to 0, it's undefined, but as approaches 0 from the right hand side, we know that this thing goes to infinity. So there's no negatives and there's no asymptote either. So we have a global minimum. And for part C, we're asked, is F convex? Explain your answers. Okay. So I got this question wrong. I thought it was convex because in the Hessian matrix, all the pivots were greater than 0. But I kind of just forgot the context that this Hessian matrix over here is just for one specific point. Whereas in order for it to be convex, it has to be throughout the function, right? It's not just at one point. So if we just kind of see the Hessian function it's not going to be the case that it's always going to be um it doesn't have to be at that case because for instance um huh I didn't include a work inside here, but the idea is basically if I have the two things, then oh yeah, I do have it here, part C here. I use what is called h of f at all. um So then I have my determinant, which is I'm checking the first element of it. This one is definitely satisfied in the first minor because it's just this value, which is positive and greater than or equal to zero. So that works out. But the problem is that when we have the 2 by 2 matrix, our determinant is this thing over here. And this thing could be smaller than or equal smaller than zero. For instance, if we have x equals to 2a and y equals to 2b, then the determinant, this thing, the left-hand side over here, would be less than 1. So then when we subtract it, this thing is less than 0. So then it's not convex in that case. So that's why part C kind of fails. It's not actually. I got that wrong because I was just referencing this matrix, which only applies for one point, not throughout the function. And then part D, I should let's read the question. Solve the constraint optimization problem, minimize f of xy subject to xy greater than or equal to 1. So your thing will have two cases depending on AB. Yeah, I jumped way too fast into like the Lagrangian multiplier method. But to be honest, because I already had from the earlier parts, I really didn't need to do this. And what I really needed to do is that I know that from earlier I already have the saddle point, and that is already the global minimum. So then I know that my minimum point is probably going to be this. Um, and this, when I evaluate it back in the original equation, leads me to the value of 3ab. So then what I can do is I know that my constraint is xy is greater than or equal to xy has the constraint says that it has to be greater than or equal to what to 1. So then xy by definition of this minimum point is ab because when we do this it cancels out properly to be a and b. So then we have two cases. When ab is greater than or equal to 1, we have this condition over here. And when it's not that case, when the minimum point is not this, then what we have is AB is smaller than 1. So in that case, it's out the minimum point is outside of our allowed region. So then that means that our minimum will be definitely on the boundary. And if it's on the boundary, that means that our xy is equal to 1. So then we can just rearrange it and say that y is equal to 1 over x. So then we're going to do some calculation, plugging it back. F of x, 1 over x, we know this from just earlier. We put it back into our original equation and we simplify it to get this. We take the derivative of this and then set this to be equal to 0 to find the minimum value. And we get that x is equal to this, and then by default, y is equal to that. So then we know that our minimum point is just basically x and y of this value, and we put it back into the original equation to get that our minimum value in this sense is this value. Okay, so this question was I definitely did not use my brain to actually think about what I should do. I just jumped into the calculation too fast. Lagrangian multiply, even though it's a useful thing that you do for most of these questions, inside here is not the best to use. So that's why I crossed out the work. Okay, so going to part E, find and classify the stationary point of the function g from 0 to infinity cubed to r. So we have this function over here. Okay, so stationary point and classify, classic question. So I have this over here. I copied out my function. I take the partial derivative with respect to x, y, and z, and I set them to be equal to 0. And then I get that my yz is equal to this, xz is equal to that, xy is equal to that. Great. And then I see that every equation I can multiply it by the respective to fit a x, y, z. So then I get this equation. I manipulate it and I get x equals 4y equals 8z. And in fact, I can just further because I know these conditions. I can just solve it and find that x is equal to 4, y is equal to 2, z is equal to 1/2. Because three equations, three unknowns, yeah, it's solvable in here, in this situation. And then now taking the second derivative, xx, yy is easy. Take it with respect to the previous things I got. I got these, and I got that gxy is equal to z, gyz is equal to that, gxz is equal to this. Okay, awesome. Basically what I did for this was just like, yeah, it's just simple algebra. And this was how I found the, what is it called? The values of x, y, z was that I used this over here. I saw that x, y, z, I just plugged each of them inside here into this is equal to z to the -1. I just did some algebra and I got z is equal to 1/2. So then now I plug in everything of x, x, y, y, z, z, x, y, y, z, x, z into my Hessian and I get this. This is my Hessian matrix. Pretty good. I'm going to just substitute in the values in terms of z, which is simple, and I get this. This is actually correct. Up to this point, it's correct. And then, obviously my brain shut off, and when I was doing calculation, I kind of just misread that this 2 here is 1/2. So then I did 4 rather than 16. So that's where I made the error in this question, is that this value should have been 16. And then I just did the classic Gaussian elimination to get this and then get this. And I get my reduced echelon form. And inside here, I see that all of the things on the pivots are positive or greater than or equal to 0. So I know that this definitely has to be a local minimum. And because from earlier I established that it's a function that is like basically it goes from infinity and it goes the other way to infinity, so there's nothing that goes further down. So then this becomes a global minimum. So I know this is a global minimum and I can classify it as the such. When I was doing this question, it's kind of I'd say unfortunate because it seems like did this completely wrong, but reality-wise, I just did a simple mistake. I knew what I was doing. The only problem is that I got everything else followed was wrong because the minute I had 4 here, I got 0 here. So that would have meant that if I did the Gaussian elimination correctly from this point, this number over here, if I did the wrong calculation from earlier, would have been negative. So then that was how I got the negative part here. And because I had both positive and negative, it would have led the point naturally to be a saddle. So that was where I kind of gone wrong because this number was wrong. So then it led to this number being wrong. So then it led to being negative and positive. So then it led me to write the answer as a saddle point. So that was what happened over here in this question. But reality-wise, it was just a simple calculation mistake. And I think relatively I know this type of question how to do it. Okay, let's end off here.